So lecture 14 is on volumetric strain. We're going to derive one of the fundamental equations of fluid mechanics in this class, and that's basically conservation of mass. Just a review of what we did on Friday's lecture. So we talked about boundary layers and how different properties that vary the Reynolds number, local Reynolds number, will affect the boundary layer thickness or boundary layer performance. We talked about how turbulent boundary layers have higher velocity gradients at the wall, so they have higher wall shear stress. I gave you this expression here. So drag force on a flat plate of length L. There's a problem in your homework this week that I recommend you looking at for the laminar boundary layer. So you're going to be doing something similar in the tutorial on Thursday, which is also on boundary layer. So the first three questions of the homework assignment will, or the homework set, I should say, will prepare you for that tutorial. So if you're okay with those questions, you should be good for the tutorial. We also talked about an interesting case where turbulent boundary layers can be induced in order to reduce the total drag on something. And that's because though turbulent boundary layers have higher skin friction drag, they can delay flow separation from a surface, and that delayed flow separation reduces the pressure drag. So that's a major source of pressure drag is when flow separates. And a turbulent boundary layer tends to separate later, kind of loosely speaking, because it carries more energy, so it's easier to remain attached to the surface. The context of today's lecture, we're getting to the end of module 2, so today's lecture is on volumetric strain. Wednesday's lecture will be on acceleration. So our learning objectives are to define volumetric strain rate, calculate volumetric strain rate for a fluid element, interpret the divergence of a vector field, and apply this condition we have for an incompressible fluid to analyze velocity fields. Any questions before we begin? Okay, sounds good. Okay, so let's start by considering like an example velocity vector field. So consider the velocity vector field. V is negative x I hat minus y j hat. So let's sketch some vectors from this field. So that black point there is the origin. We're going to draw vectors for this vector field. So they'll look something like this. So they start small, and then they get longer as you go away from the origin, but the vectors point towards the origin. So here's an example vector field, a velocity vector field, we can call it. Does anyone have any comments on whether they think this could be a valid vector field for a flow field? Yes, so nothing will be moving, but so we have velocity vectors, right? So things are moving. But you're right. So what would happen at the origin is the key issue here. Yep. Do you have a comment? Sorry. Yeah, so it depends on the z direction. That's good. So if we had a z direction, you could say, oh, okay, maybe they all come to a point, but then they go out. It's like a very weird vector field. They go straight out. But if we don't have a z component, this doesn't really make sense, right? So like Aaron said, the velocity all just comes to a point, but where does all that fluid that was transported to that point go? So in fact, this isn't, we'll show later on, this isn't a valid flow field for an incompressible fluid. And in this lecture, we're going to figure out why. So this is not valid incompressible flow field. And in this lecture, we're going to see why. So I'll start by defining this volumetric strain rate. So in words, it's the rate of change of volume. So say dV by dt, how fast the volume is changing, but per unit volume. So this is the definition of volumetric strain rate. Okay, so dV by dt. So the V with the ticks I'm going to use for volume. So the top of that is the rate of change of volume, and the bottom is the volume. These are not partials. This is just a regular derivative of V with respect to t. So this is the definition of volumetric strain rate. So over the course of this lecture, we're going to build up some intuition for what this is and what it looks like for a fluid parcel. So don't worry too much right now if this is a little bit confusing. So let's start by here. So we're going to start by considering some fluid in a tank. Say we have this tank here. Say we have one inlet and one outlet for this tank with some fluid in it. So say this tank is filled to here, that level with some fluid. So we have one inlet and one outlet. So the inlet flow rate, volumetric flow rate, we'll call V dot in. The outlet we'll call V dot out. So we have some tank with some amount of fluid in it with an inlet and an outlet. That's the only way the fluid can enter or leave the tank. So this is going to sound like a simple question, but how do we change the level of liquid in this tank? Yep. Exactly. So we change the level of liquid in the tank using a difference of volumetric flow rates in and out of this tank. So if, say the diameter of those two pipes are, oh, I didn't draw V dot out arrow. So say the diameter of these are equal. The only way we have to change the volume flow rate then is a difference in velocity. So dV by dt is V dot in minus V dot out. So if that's positive, it's filling. And if it's negative, it's draining. To change volume, we need a difference in velocity. So this is a more easy to understand example of how a difference in velocity creates a volumetric strain rate. So this dV by dt, if we normalize that by volume, that would give you the volumetric strain rate in the tank. So we can affect the volumetric strain rate by having some sort of difference in velocity. So now we're going to zoom in to a very small element of fluid and see what this looks like, kind of a differential case. So consider a small volume. So assume we have some small volume of fluid here. I'll define our coordinates that we're going to use as that z there. Okay, so this volume, we're going to call the length of the volume L1 in the x, L3 in the z, and L2 in the y. Okay, so this is at time t0. Then the volume of that box it's a cube, so it's just L1, L2, L3. Let's say over through some, I guess, process or over a small change in time, the volume of our box changes. So this is our new, it's the same, I guess, volume, but we're going to say the volume has changed. So the length is now L1 plus some delta x, L3 plus delta z, L2 plus delta y. And the time for this is t0 plus delta t. And our new volume is, again, still just length times width times height. So L1 plus delta x, L2 plus delta y, L3 plus delta z. Okay. So the change in volume of this box, we'll call that delta V. That's V at t0 plus delta t minus the original volume. So if you work this out, I'm not going to work it out because I don't think you guys want to see me work this out, but it's L2, L3 delta x plus L1, L3 delta y. It's L1, L2 delta z plus a bunch of terms that we'll just call higher order terms. So for example, L2 delta x delta y. So we're going to say we have a really small volume, so delta x is already really small. So like delta x delta y is negligibly small. So we're going to basically neglect the higher order terms and just take our linear terms. So this delta v that I've written here is just what happens when you multiply that out and subtract this. Any questions on where this came from or what I've done so far? Okay. So now the question I have is what causes these changes in length along each of the coordinate axes? So what causes delta x, delta y, and delta z? So if we're following this in a Lagrangian perspective, if we're following this parcel of fluid as it moves through space, what causes the, what's one way that we could cause the change in length of this element? Yes, please, Aaron. High pressure to low pressure. Okay, so applying different pressure on the different sides of the element. That's a good answer. Yeah, I guess maybe more related to this example up here. So I guess I'll come back to your answer later. So related to this example up here, what could cause a difference in volume of this element? Yes, please. Change in velocity. So if we had velocity on one side of this cube that was different of the velocity on the other side of this cube, it would stretch. The cube would stretch. Okay, so the answer is a difference in velocity still. Okay. This is going to look a little similar to what we did when we were doing the pressure force derivation, but I'm going to explain it in a little more detail this time. So let's look at let's look at just the x direction first. So let's look at our cube. We're looking basically at this front face of the element. So we're looking at this face here, this face here. Okay. So on the left face, this element, we're going to say we have some velocity u. And on the right face of the element, the velocity will be that original velocity plus the change in velocity per unit length in the x direction times the length in the x direction. So the length of this element is L1. This is similar to what we did with the pressure. So I'm going to write out the explanation of this. So here's how we got, I'm trying to explain basically how we got this now. Okay. So I'm going to plot this function, say, along the x direction, u as a function of x. So at, say, x equals 0. So you can imagine this being the edges of our box, the blue. The blue is our box, right? So the length of that box is L1. So we assume kind of a linear variation here. And the slope of that line would be given by partial u by partial x. So all we do to get the velocity on the right-hand side, assuming we have this linear variation, is just add whatever we got by moving L1. So this will be u plus partial u by partial x L1. So I drew something similar like this when we were doing the pressure derivation, but I think this one is much neater. So that's how we got u plus partial u partial x L1. Any questions about that? Okay. Okay. So now we can figure out what that delta x is because we know the two velocities. So delta x is going to be basically the change in length there is going to be the velocity at the right face minus the velocity at the left face times delta t. Again, this is just basically distance is velocity times time. So as this thing moves, the difference in velocities will cause it to stretch in x, which is delta x. We know what those velocities are by that kind of above sketch. So this is just partial u partial x L1 delta t. You can do the same thing in the y and z direction. So we get delta y is partial v, partial y, L2 delta t, and delta z, partial w, partial z, L3 delta t. Okay, let's just, I guess, sorry, I'll let you guys finish writing that. I just want to zoom out for a sec just to confirm where we're at kind of in what we're trying to do here. We're trying to compute the change in volume of this element as it moves in terms of the velocities. And what we see is that the change in volume is going to be related to these partial derivatives of the velocities along x, because the difference in velocity across the fluid element will cause it to stretch. That's what volumetric strain is. So see, we related here just delta V, so the change in volume. These are all lengths. So L2, L1, L3, delta X, delta Y, delta Z, those are all just lengths. So this is all spatial lengths here. Now we have an expression of these lengths in terms of the velocity derivatives, because the length that stretches is related to the velocity gradient. Are there any questions? Yep.
For the parcel, when we look at the change in that velocity or that gradient, we're stating that the length is fixed. But then isn't there a relationship between the velocity changing with the length itself? So like,
Yeah, but it's kind of higher order, so it can be neglected. It's a good question. So like, how can you have, if you say partial u partial x, well, like your partial x now actually is a little bit longer. Yeah, so we don't worry about this. This is kind of like an infinitesimal scale.
okay.
So, and this is also instantaneous. So yeah, it's a good question, but we don't need to worry about it. Any other questions? Yep, please.
Sure, but you keep saying like it'll expand and stuff. So you went back to the example of the cylinder.
Yeah,
In that case, it's only going to go.
exactly. Yeah. So we're getting to the point where we'll see why this difference in the velocity in the x direction could actually affect something in the y direction. So we're getting there, but good question. So this question was about like the difference in velocities here, but the x is fixed, right? So we have to change in y. So it's a good point, but okay. Okay, we're really close, so just bear with me for a couple more minutes. Okay, so let's go back to that expression we have for the change in volume. L2, L3, delta x plus L1, L3, delta y plus L1, L2, delta z. This is just the expression we had above. And I'll plus the plus dot dot dot, but we're not going to worry about the dot dot dot. Okay, so this expression for delta v is just the same expression I had up here. Okay, so I'm just copying this so we have it for reference. Now let's replace those delta x's with the expressions we just derived. So L2, L3, partial u by partial x, L1 delta t, plus L1, L3, partial v by partial y, L2 delta t, plus L1, L2, partial w by partial z, L3 delta t. Okay. We get delta v. So we're going to collect our, basically we're just going to factor this expression. So we get partial u by partial x plus partial v by partial y plus partial w by partial z times L1, L2, 3 times delta t. Okay, So I think you guys know what this part of the expression is, so I'm not going to ask you that. Does anyone know what this part of the expression is here? The first part, the term with the derivatives in it. So partial u, partial x, plus partial v, partial y, plus partial w, partial z. Yep. Mm. It's the sum of the change of velocities along each axis, right? So there's a calculus term for this. Divergence. Yeah, exactly. So this is the divergence. And you can write this as nabla dot v. Okay. So I'm going to rearrange this expression to get our volumetric strain rate. And we're going to let the deltas kind of go to the infinitesimal scale. So we have the deltas would turn into d's. Okay, so we get 1 over v dv dt. So our volumetric strain rate equals partial u by partial x, partial v by partial y, partial w, partial z. Okay, and like I said above, that expression is equivalent to just writing the divergence of the velocity field. So now we can calculate with a velocity field, basically the volumetric strain rate of a fluid element. And that's a local kind of strain that a fluid element will experience. And all that strain is at the end of the day is it's just the sum of the changes in velocities that it feels along the three different axes. Okay. We have a very special type of flow that we're going to use all the time in this class, and a lot of real engineering fluids are this type of flow. So we'll define incompressible flow. So in an incompressible flow, we have a constant density. And that means that since density is mass over volume, if the density is constant throughout your flow, you basically have a one-to-one relationship between mass and volume. Kind of like volume is mass, all you do is multiply them by a scalar. That doesn't change. So this is kind of like a mass strain rate now, or conservation of mass. Yep. Good question. Okay, so that delta t, I move it over here under, so this would delta v over delta t, and then we just let the limits go. Yeah. So since in an incompressible flow, density is constant, that means that volume and mass, they're basically the same variable, just differing by a single scalar. And we know that mass is conserved. So since mass is conserved and mass and volume are basically the same thing, just with a scalar difference, that means that volume is conserved. You can think of it that way in an incompressible fluid. So that means, I'm going to write it in words, then write it in the math. Volume of a fluid element does not change. So since the mass of a fluid element doesn't change by conservation of mass, the volume can't change. Okay, so then math is just basically that we have zero volumetric strain rate everywhere in our fluid for an incompressible fluid. Sorry. This is velocity v equals 0. So these say the same thing. One of them is just with math, and this has a special name. So this is called the continuity equation. The way I've written this equation here is for an incompressible flow. So in fluids 2, you'll see this equation is different for a compressible flow. But if you take that generic one and assume it to constant density, you arrive at this equation. So this is the divergence of the velocity field as 0. So the divergence of the velocity field is the sum of these three terms here. So this means if you have a difference in, say you stretch in x, it elongates, it has to shrink in y because the total volume has to stay the same. This is kind of familiar from a little bit from solid mechanics. So you kind of pull on it, it causes a stretching along a different axis. So with that tank, there's a difference in velocity in the x direction, but by the continuity equation, since the volume doesn't change along the x direction, since the size doesn't change, it has to change along the other directions. So in this case, it would be the y and z direction. Well, I guess in this case, the z direction is also not changing. So therefore, the y direction has to take all of the change because the volume of each fluid element can't change. So the sum of the entire volume can't change either. Okay, so this is basically conservation of mass for a fluid, for an incompressible fluid element. Okay. So usually in practice, we'll come back to this multiple times and you'll see it in fluids too. We determine whether a fluid is incompressible based on the Mach number. And usually people take 0.3. So if you're going less than Mach 0.3, you're incompressible. So before I move on, are there questions about the continuity equation or this incompressibility? Incompressible. Yes, please. Yeah. Hmm? Not necessarily. So yeah, the Mach number is just the speed of sound. So you can have a speed of sound, say in water or in like a gas. So for example, a liquid pipeline like that does water or oil would usually be considered incompressible. But a gas pipeline that transports gas is a compressible flow because it's gas, so the Mach number is a lot different. Yeah, so the Mach number is usually, we hear it in the context of aerodynamics and cars and that stuff. Well, maybe not so much in terms of cars, but yeah, we hear the Mach number a lot in aerodynamics, but it exists for any flow. So we'll talk about what that is later on, but it does exist in any flow. It's just about the speed of sound. So you're like, oh, well, how can we hear sound in certain fluids? So the speed of sound is basically the speed of which information can be transferred in a fluid. So a small pressure perturbation can move through a fluid at that speed. Sorry, at the back, I saw you had a question there. Yeah. Yeah. Okay. We'll define the Mach number later, and so you're not going to be asked about the Mach number until we define it. I just want to give you this when we see this for completeness. So any questions about this? Okay. Just for clarity, I want to clear up the difference between the divergence and the gradient. So this nabla is a vector, and it's an operator. So it's partial by partial x, partial by partial y, and partial by partial z. So you can think of it as a vector operator. Okay, so when you do a dot product of nabla with something, that's the divergence operator. When you just operate directly on something, that's the gradient. So the common example we have in fluid mechanics is what I just gave, so the divergence of the velocity. Gradient, we've seen this before. So gradient of pressure. Actually, I'm going to write those in red. So this operator, the divergence operator takes a scalar, takes a vector. The gradient operator, in this case, will take a scalar. So the divergence operator takes a vector and returns a scalar. The gradient operator takes a scalar and returns a vector. So the divergence kind of decreases the rank. So say you take this isn't, you won't do this in this course, but say you take the divergence of a matrix, you get a vector. And if you take the divergence of a vector, you get a scalar. The gradient kind of goes the other way. So you take the gradient of a scalar, you get a vector. You take the gradient of a vector, you get a matrix, and so on and so on. In fluid mechanics, we generally deal with scalars, vectors, and matrices. And anything higher order than that tends to be a little bit niche. So any questions on the operator with Nabla here? So the continuity equation is not a vector equation. It's just a single scalar equation. There's not three equations here, even though we have vectors. It's a dot product, so this is just one equation. Okay. So the divergence operator, roughly speaking, represents sources or sink terms in physics. So there's a video I've played here from 3 Blue 1 Brown about divergence.
Take a look at this vector field and think of each vector as describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness, as if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness. The divergence of a vector field at a particular point of the plane tells you how much this imagined fluid tends to flow out of or into small regions near it. For example, the divergence of our vector field evaluated at all of those points that act like sources will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction, since that would still insinuate a certain spontaneous generation. Now on the flip side, if in a small region around a point there seems to be more fluid flowing into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in two-dimensional inputs and spits out two-dimensional outputs. The divergence of that vector field gives you a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative, and that output is just a single number, measuring how much that point acts as a source or a sink. I'm purposefully delaying discussion of computations here. The understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one used to illustrate an arbitrary vector field, then if that fluid is incompressible, the velocity vector field must have a divergence of zero everywhere. That's an important constraint on what kinds of vector fields could solve real-world fluid flow problems. For the curl at a given point, you also think about the
Okay, we're not going to do curl now. Trust me, you'll thank me later. Okay. So anyways, the divergence is about sources or sinks. Basically, you can't have a source or a sink of mass in a fluid. So the divergence of the velocity field everywhere is zero. So we're going to do a bunch of examples now. Any questions about that video before I get into examples? No? Okay. So let's take the velocity vector field from the start of the lecture. That was negative x I hat minus y j hat. So this was the vector field from the start of the lecture where everything goes into a point. We said that's not really physical. Where does all that mass go if it doesn't go out of the plane? So the divergence of this is a 2D field, so the divergence is partial u partial x plus partial v partial y. So that's minus 1 minus 1 minus 2. So that's not 0. Therefore, that's not a valid incompressible flow field. So any questions on that? So basically we have a sink, a uniform sink, since the field is kind of linearly dependent. So it's just a sink everywhere of -2. So it's not just at the origin, like this doesn't depend on x. The sink is everywhere. So it's clearest at the origin where everything coalesces to a point. But out here, say on some fluid element out here, we're also sinking mass. So the stretching in one direction isn't equal to the shrinkage in another direction. You can think of it that way. That's what the divergence tells us about that field. So it's not a valid incompressible flow field. So this is most often seen as a constraint on incompressible flow fields. Any questions on that? No? Okay. I'm going to do another example here. Okay, so let's take xy is 5x squared y I hat minus 5xy squared j hat. So before I start, let's have a pop quiz. So maybe let's do a raise of hands. So who thinks this is a unsteady flow field? No hands? Good. Okay, yeah, it's a steady flow field because there's no dependence on time. Right. Okay, so let's just check if this satisfies the continuity equation, aka is it a valid incompressible flow field? In order to answer that, again, we're just going to check the divergence of the velocity field. Which is partial u partial x, partial v partial y. So can someone help me? What is partial? So this is u. So what is partial u partial x? 10xy. Okay, and what is partial v partial y here? So again, this is v. Yeah, I kind of vaguely heard it. So 10xy minus. So then minus is included in v. So that's equal to 0. So yes, this is a valid. In terms of the continuity equation, which is one of the constraints our flow field has to satisfy, we can say this is a valid incompressible flow field. Okay. We're going to do one more. Actually, we're going to do two more. So v is sine t I hat plus cos t j hat. What is the divergence of this? So now, the previous one, we had no t in our velocity vector field expression, so it was steady. Now we do have a dependence on time. So by definition, this is an unsteady flow. So the divergence of this is still partial u partial x plus partial v partial y. So what is partial u partial x? What is the partial derivative of sine t with respect to x? Anyone wants to guess? 0. Yes, it's 0 because there's no x dependence in here. So this is both 0 plus 0 because there's no spatial dependence. So though volumetric strain rate is defined as a rate of change in time it actually only depends on the spatial variation in the velocity field for an incompressible flow. So we could say this is a valid incompressible flow field. Now, the more complicated versions of these questions usually involve, they give you one component of the velocity and you're asked to determine the other component. So we're going to try one of those now. So let's say we have some velocity field u pi hat plus v j hat plus w k hat. And we're given u equals a x squared minus y squared. We want to determine v, and we're given w is b. So a and b are constants. So we're given two of the components, and we want the third one now. We're still going to apply the same. So basically, the question is, what is the form of v for an incompressible flow? So since it's incompressible, we know the divergence velocity field is still 0. And that is partial x plus partial v by partial y partial b by partial z. So partial b partial z, since b is a constant, is 0. And we're left with this expression here. So 0 is 2ax plus partial v by partial y. Okay? So we rearrange this for partial v partial y. So all we've done is just applied the continuity equation to the velocity vector, with leaving our partial v partial y as an unknown. So we know that the partial derivative of whatever v is with respect to y gives us that. So now we integrate this, we integrate a partial derivative. And in order to do that, we kind of assume that we're just going to integrate y like in terms of y. So our constant now could depend on other variables. So this means that v is negative 2axy plus some other function f, where f could depend on all the other variables except y. So x, z, t. Okay? So all we know by the continuity equation is just the partial derivative of whatever v is with respect to y looks like that. But since this function, the partial derivative of this with respect to y would be 0, we're not actually able to solve it. So from the point of view of continuity, f is arbitrary. From the perspective of the continuity equation. So from that perspective. Meaning that whatever f is, f could be some crazy complicated function. As long as it's not some complicated function of y, this will still satisfy the continuity equation, and therefore mass will be conserved in this flow field. Any questions about these three examples? These are kind of a similar type of example you'll see on the homework, and pretty typical like continuity equation type questions. I'll just summarize again. The continuity equation tells us stretching in one direction. If you go stretch in one direction, you've got to shrink in the other direction in order to keep volume constant. And all we do is just sum the partial derivatives. So it's a simple equation, but it's quite powerful. It tells us about mass conservation this form does in an incompressible fluid.